Hey everyone, welcome back to my channel. In this video, let's whiteboard a distributed cache, something similar to Redis. So let's try to first understand what are we actually building. So what we want to build is that in a distributed system where we have a huge scale, lot of number of parallel requests being being sent by the server, we want a cache which is able to help which is able to serve our application. So let's try to think what we are building. We are building a distributed cache which is able to help us set a key value pair, get a key value pair, and delete a key value pair. And we want this distributed cache to be able to serve multiple server nodes that we might have in a single application. And we want this distributed cache to be in front of our database. So we want to protect our database from a stampede of requests, and we want to make our system more basically maybe low latency, or it could serve multiple purposes. But this is what you want: a cache which is able to stop all the traffic going from the database and handle some of the requests going to our database. But what do you think? Why is this problem interesting? And why would it actually be difficult? Why a single instance? Why do we call it distributed? There's a reason why we are calling this cache distributed, because we want multiple nodes of cache being able to act as one single cache and able to handle 100k requests per second. And we also need very low latency, less than 10 milliseconds. And we also want to be able to handle data which might take up to 1 terabyte of memory, which is not possible to be fit in one machine's RAM. So therefore, that's why we need to spread it and use multiple nodes for it. The third requirement is that if one instance dies, we don't want our entire system to be unavailable for us. So that is why we want multiple nodes. In case one box crashes mid request, the cluster would still be available. And we also want to handle the problem of hotkeys, where if we have multiple keys and one key gets all the traffic, huge traffic, then we don't want a single node being just overloaded because of the huge traffic. So we want to design our system in a way that if we have one viral key, our system is able to handle it gracefully. So next, let's try to understand what are the functional requirements of our system. So the functional requirements are similar to what we have in a basic cache. We want to be able to set a key, get a key, delete a key. That would be the whole three functions that we want. We also want to add a time to live TTL to each key, so that in case we want the key to disappear after a certain time, so we want this TTL feature available as well. And thirdly, we want, in case our memory is full, since it's a cache, we want some sort of eviction mechanism so that our memory gets cleaned up. So we would use LI eviction, which means its least recently used key would be dropped. Now let's see what are the non-functional requirements that we are going to handle in our system design. The first one is 1 terabyte of cached data, and the second one is 100k requests per second, and the third one is less than 10 milliseconds get and set, which is for the P99 request. So we usually follow the metric of P99 and P95 and P99. So we want less than 10 milliseconds of P99. The fourth non-functional requirement would be that our system should be highly available. That means if one node goes down, the other node should be able to handle the remaining traffic, and somehow it should be, data should be replicated, so we should not lose data if one node goes down, the other nodes should be able to handle those requests. And since we want our system to be highly available following the cap theorem, In case we want high availability, then we might have to compromise on eventual consistency, which is fine. Some things that are out of scope is durability. We do not expect strong consistency because we expect eventual consistency. Then we don't want to care about any rich queries, transactions, or anything. We simply want basic requirements where we are the memory ceiling is 1 TB, 100K requests per second, and less than 10 milliseconds should be the latency. P9 latency of get and set both. Now, what are the core entities in our system and how does one node store data? So, if we look on a high level in a cache, what are the entities? First, we have a key, then next we have a value. Third, we need to associate some metadata with the entry, for example, TTL, and all of that we need to store in a hash map. And then we want to apply some sort of eviction policy. So that becomes the fifth core entity in our system. What are the APIs that we want for our cache? The APIs are very basic. We want a get key API wherein we are passing a key value and the cache should be able to return the value or null in case it's a miss. Set should be the second API that in case we want to save a key value pair, we have the set API and we also want an optional parameter of TTLs in case the TTL is not provided. So we can either keep it some default value and then we do not, or the second is we do not add any TTL. Not adding a TTL usually does not is not a good design for system design, but it may also vary on your requirement because since we have LRU eviction, so even if we don't add a key, either if the key is getting used a lot then it's fine, but if it's not getting used a lot then anyway it would be evicted by using LRU eviction policy. And the second problem could be if you don't apply a TTL that the data might become stale. So ideally in ideal scenario it's always good to have a TTL associated with every key. So in case the TTL is not provided, keeping TTL optional, so we can just add a default value. So in case we do not provide a TTL in the API, the server assumes the default TTL. The third API key is the delete key. So what do we want in this is that if the cache gets this request, this API call, then the cache just needs to delete that key. We ideally want to make it idempotent. So in case we miss deleting the key, basically the key does not exist, we still return OK. So we don't want client to know that the key existed or not. We just want to return OK response. And that was similar for set key as well. It is also idempotent. So if we try to set the same value again and again, we only get a response OK. There is no other response. And if the key already exists, then we silently override. We don't want to let the user know that this key already existed. So now let's try to solve this design and think through what all would be the components of this design. Since we want to make a cache, let's assume for a distributed cache, also we try to use a single cache server. So assume this is a cache servers. We have application server. They are calling the cache server, and here we have the database. So cache is stopping all the read requests before the database and serving the application server. But what happens if this cache goes down? What happens? First problem that we knew is what we want to be able to handle 1 terabyte of storage. It's not possible for one box to be able to serve us such a high memory availability. The second is we might be not able to serve the 100K requests per second. Now let's see what would go wrong if we just use a single cache server. If you use a single cache server, what do you think are the problems? There were certain functional requirements that we were trying to solve, which was 1 TB of data. Do you think one box, one single server, one single machine can let us fit in so much amount of data? And in case it does, then searching through all this data might get problematic. Although Redis is single threaded and it is very fast, but there are still certain limitations that Redis has. 1 terabyte of data being served by one single box of RAM can become problematic. The second problem is that it can act as a single point of failure in our system design. So if this server goes down, all the requests would go to database. That means if cache is available, our database might not be able to serve the entire traffic. It might be a huge read traffic, and the system might just get overwhelmed and crash. Third problem is similar to this. If it's a single point of failure, similar if it dies and it restarts, then we would have cold start stampede, which means that if a server machine restarts, then the server is empty. So because it's inbuilt RAM, so it just gets empty. Then every request that is coming goes to the database. So that becomes a problem. That's why, because it's a huge number of requests that get hammered to the database. That's why we call it a stampede. So that is another problem that can happen. The fourth problem that can happen is our requirement was to be able to serve 100 requests per second, 100k requests per second. One CPU won't let you handle such high amount of RPS. So that is why these are the problems that a single cache server would make us face in the system design. So let's try to see how we can improve the system design. So what if instead of one single cache server machine, we use multiple cache machines, and we are not storing each and every information in each node of this cache, distributed cache. We are sharding the cache. What does sharding here means? If we are storing keys from A to Z, we are making each node only store keys up till a certain range. For example, A to Z go in A, I to P go in B, Q to Z go in C. This is just an example, but this is how we are designing our system. So we are basically sharding the information goes inside these cache servers. And what happens then? So whenever a request for a key goes in, that we want to search for, we want to get the value of this key. So the client would know somehow the logic how which shard needs to be hit for this key, and then it sends the request to that shard and gets the response back. In this way, our database still gets saved and the requests are served via the Redis, via the distributed cache, and not the database. Now, next, let's see how it is helping and how is it designed. How can we use multiple nodes in a cache cluster? So, one of the most effective ways to deal with multiple nodes in such a case where we have where we have applied sharding for over range for the multiple nodes is consistent hashing. It's a nice technique which is an advanced version of hashing. Hashing is basically when we apply a formula based on the number of what do we say number of keys that we have, and based on the formula we do a modulo and then we get a node value which is corresponding to the shard value. And what consistent hashing does is we arrange all the nodes inside the cluster in the form of a circular ring. So it's not literally in a circular ring, but it's visually like it's virtually we are building a circular ring, so that conceptually all um, the keys stored falling in this range are stored in the shard next to it. So all the keys here would be stored here. The next shard all the keys in this range would be stored in the next shard. So what is the advantage of this is, so it basically helps us in better redistribution. So in case one shard goes down, we don't have to redistribute all the keys. We only need to redistribute these three keys. For example, in this goes on, these three would be assigned to this. And in case a new uh, shard also comes up, then again we don't need to um, redistribute all the keys. We just need to redistribute a small subset of keys. So that is the main advantage of consistent hashing and why it's preferred. So the best way to represent all the nodes inside this distributed cache is consistent hashing. So this was one level of improvement in our cache system where we added multiple nodes, and how we distributed the multiple nodes was using consistent hashing. The next challenge is how does the data gets replicated, because we want to also ensure high availability. So next we want to see how the system enables the data to be replicated, and what happens if one server goes down, and how does the entire system work for failure handling. So first thing is about replication. So when we have multiple shards, for each shard we'll have multiple nodes. So one would be the shard leader, which is accepting all the writes on the cache of that node. And then we would have multiple, let's assume just two replicas. We have two replicas which is serving as a read replica. So whenever a set call happens, it happens in this shard, and whenever a get call happens, it happens in these two shards. Now how do these three replica work? Basically it works on a leader non leader follower uh, mechanism. So the the shard which is the leader writes them, and the other two, which are the replicas, they are the followers. So at any given point of time, if one of the node fails, if replica 1 fails, replica 2 fails, it will make a copy of the leader node and build its data. In case the leader itself goes down, then one of the these two replicas would be promoted as the write a replica till the time a new replica comes up. And if when the new replica comes up, it becomes a read replica. It does not mean that that one only has to be the right replica. Mainly, one of the one of the three nodes has to be a write a replica, which is the leader, and the remaining two remain the follower. And how this leader selection happens is a different concept altogether. There are some algorithms like Paxos and Raft, which are followed for this um, leader election. These two algorithms are out of scope of this video, so maybe we can cover them in one of the future videos. But these are the algorithms that are followed for leader election. How the nodes know that if they die or they do not die, or how the leader or how the leader knows that the other two replicas are working is using a heartbeat mechanism or the Glossop protocol. So heartbeat mechanism is that they are simply sending a ping to each other, wherein with which they are determining that all these peer nodes are alive. In case a heartbeat gets missed, then the peers assume that the node has died and they try to spin up a new node. Like that spinning up is part of not the actual mechanism. It depends on what we are using for containerization. So usually that is taken up by if you use something like Kubernetes. So that is something that takes care of this. But if to understand the protocol, this is a protocol that is followed. Next, let's talk about consistency and the trade-offs that we had to make since we decided our system has to be highly available. We discussed this earlier in the video as well. So, since our system is highly available, so based on CAP theorem, we will have to compromise on consistency. And for cache system, we are okay to follow eventual consistency. So that means within 1 or 2 seconds, uh, our all the replicas would have the same data. So we would write to leader, and the replica lags might replica might lag by a few seconds or basically few milliseconds, so it's okay, and the read might be stale. It is fine, no problem in that. The next question could be, though we are using multiple nodes for this distributed cache, but which database to use? Should we choose Redis or Memcached? So my choice would be Redis because Redis offers a lot of extra features. For example, the first advantage of Redis is it offers us multiple types, whereas Memcache is only key value pair. It's only string based. uh, Memcache is slower than Redis because Memcache is multi-threaded. Redis is single-threaded. It follows the event loop architecture, which keeps it locked free, and that is why it is so um, fast as well. And why should we choose in-memory keyword? Because um, RAM access is millisecond, which helps us follow that 10 milliseconds, less than 10 milliseconds low latency non-functional requirement. So that is why we choose in-memory key value pair. So let's see how the final architecture looks like. We have a client which is sending us the request. We have a consistent hash ring which is facing the logic of our multiple shards of cache nodes. Our cache is placed in front of the database. Our client sends in some request from the consistent hash ring. We know which node we need to save that request or get that key value of pair from. We have, for each key we have multiple, for the database, for the cache we have multiple shards. Each shard serves us only a key of a range of keys. Each shard has multiple read replicas. The shard which is the leader shard is the node which serves the write request, and the other two replicas are the one which serve the read replicas. In case one node goes down, one of the other nodes takes up its place. In case the leader node goes down, if any read replica goes down, then based on gossip protocol or heartbeat mechanism, the other nodes get to know that one node is down and they spin up a new node. Let's also try to understand how a get flow works. So a client sends in the request with the specific hash where the shard would go. The hashing would try to route the request to that particular shard. In case the shard does not have that value of the key, it would hit the database. The database returns the value gets stored in the cache, and then the cache returns the value to the client. This is how a particular data flow in a get key and a set key would work. So in the get key itself, we are doing the set in the cache as well. So if I have to summarize the entire system architecture that we designed in just 6 lines, I would put it like this. So our distribute cache is one hash map which is sharded, which has separate placement for per node storage. In case our one of the node gets down, one of and we have some sort of redistribution in our uh, cached cluster, then only one by nth of the keys are redistributed. We don't need to affect all the keys. In our shards, replicas scale the reads, and we have one node for as a leader node for the shard, and async replication happens inside that cluster, and it makes our system highly available. But the trade-off is that there might be some staleness in the read data. The cache is in memory store, so it is disposable. The actual source of truth is the database. We use cache only to save some requests going to the database, not some, a huge portion, mainly to serve the read traffic. And basically it consists of a hash map plus a double linked list with the O of one time complexity for get, set, and event. So this was our entire system design for distributed cache cluster. If you got to understand something in today's video, do like, share, and subscribe, and do put it on the comments any other system design that you want me to whiteboard next. Till then, goodbye. Take care.